Right now, as you watch this, trillions of cosmic mysteries swirl just beyond our reach, places where the laws of physics unravel, where light itself gets swallowed, and where the universe whispers secrets we may never fully understand. Think about that for a second. We live in a time where humanity has mapped the deepest oceans, cracked the code of our own DNA, and even sent robots to Mars, and yet, vast stretches of the cosmos remain utterly, tantalizingly off-limits. It's not just a matter of distance or technology. It's as if the universe has drawn invisible borders around these regions, places so bizarre, so hostile, or so enigmatic that they defy exploration entirely. That's what makes today's journey so thrilling. We're diving into 25 of these forbidden cosmic frontiers, areas where even our most advanced probes can't venture, where telescopes see only riddles, and where the fabric of reality behaves in ways that make scientists pause and rethink everything. Picture a void so empty it warps time, or a cosmic storm so violent it rips atoms apart. Imagine regions where space itself is stretched like taffy, or where ancient energies lurk, waiting to rewrite the rules of existence. These aren't just hypotheticals, they're real places scattered across the universe, each one a locked door with no key in sight. So why does this matter? Because every one of these unexplored realms holds clues to the biggest questions we've ever asked. Where did the universe come from? What's hiding in the darkness between galaxies? Are we alone? By peering into these cosmic no-go zones, even from a distance, we're piecing together a puzzle billions of years in the making. And here's the wild part: some of these mysteries might never be solved, but that's the beauty of it. The universe wasn't meant to give up its secrets easily. So buckle up, we're about to tour the edges of the unknown, where science meets the unimaginable, and where every discovery feels like stealing fire from the gods. The first stop on our journey into the unexplored takes us to a place so powerful, it's bending the motion of our entire galactic neighborhood. Meet the Great Attractor. Hidden behind the thick veil of stars, dust, and gas in the Milky Way's plane, this colossal gravitational mystery sits in what astronomers call the zone of avoidance, a region so obscured by our own galaxy's glare that telescopes practically go blind trying to study it. Think of it like standing behind a blinding spotlight while someone whispers to you from the other side. You know something is there, but the details. Utterly elusive, and yet we've felt its pull. For decades, scientists watched hundreds of galaxies, including our own, streaming toward some unseen force at millions of miles per hour, like cosmic rivers drawn to an invisible waterfall. What could possibly have that kind of gravitational muscle? One leading theory points to a supercluster of galaxies, a monstrous knot of matter so dense it warps spacetime itself. But here's the twist: even that might not be enough to explain the numbers. Some researchers argue there's something even stranger at work, like dark flow, a controversial idea suggesting the Great Attractor might be part of a structure beyond our observable universe, tugging at us from realms we can't even see. Imagine that, a force so vast it defies the very boundaries of the cosmos we know. And yet, because of our unfortunate position in the galactic backseat, we may never get a clear look at it. New radio telescopes are peeling back the dust, revealing faint glimpses of galaxies hiding in the attractor's shadow. But until we find a way to peer through the Milky Way's cosmic curtain, this enigmatic heavyweight will keep its secrets pulling us forward, quite literally, into the unknown. Now we arrive at one of the most unsettling cosmic mysteries, the Boots Void, a gaping hole in the universe so vast it could swallow thousands of Milky Ways without a trace. Picture this: a spherical region spanning 330 million light-years, containing almost nothing. No galaxies, no stars, just nothingness. Astronomers call it the Great Void, and its very existence shouldn't be possible. The universe, after all, is supposed to be speckled with matter everywhere, like a finely woven tapestry. But here, the threads have been cut, leaving a blank spot that defies all expectations. Why does this void rattle scientists? Because according to our best cosmological models, structures this empty simply shouldn't exist. The Big Bang's afterglow left behind subtle density variations, tiny ripples that grew into galaxies and clusters over billions of years. But the Boots Void isn't just a quiet neighborhood, it's a ghost town. Statistically, it's like rolling a dice 1,000,000 times and never landing on 6. Some researchers speculate it might be the result of smaller voids merging, like soap bubbles combining into one giant emptiness. Others whisper about even wilder possibilities. Could this be evidence of an alien civilization so advanced they've harnessed entire galaxies, leaving behind a dark footprint? It sounds like science fiction, but when faced with the impossible, even fringe theories get a second look. Here's what makes the Boots Void even stranger. It's not completely empty. A handful of lonely galaxies drift through this cosmic desert, isolated like oases in a wasteland. These stragglers might hold clues. Are they survivors of some cataclysmic event? Or did they form against all odds in a place where galaxies shouldn't exist? Every telescope trained on this void brings more questions than answers. It's as if the universe is teasing us, showing just enough to keep us guessing, but never revealing the full story. And that's the haunting beauty of the Boots Void. It doesn't just challenge our understanding of space, it dares us to rethink what's possible. From the eerie emptiness of the Boots Void, we plunge into a cosmic spectacle right in our own galactic backyard, the Fermi Bubbles. These towering structures of scorching hot gas and high-energy gamma rays stretch 25,000 light-years above and below the Milky Way's core, like a vast hourglass of pure cosmic fury. Imagine holding up two gigantic balloons, each one bigger than our entire galaxy's visible disk, glowing with the aftermath of some unimaginable explosion. That's what we're dealing with here, and the wildest part, these bubbles are invisible to the naked eye, lurking just beyond our ordinary perception until NASA, a Fermi satellite, spotted their gamma-ray signatures in 2010. So what could possibly create such colossal energy? The leading suspect sits at the very heart of our galaxy, Sagittarius A star, the supermassive black hole with 4 million times the mass of our Sun. Some scientists believe these bubbles are remnants of a past feeding frenzy, a time when the black hole gorged on nearby gas and stars, belching out jets of high-energy particles like a cosmic dragon. The timing fits. Evidence suggests this outburst happened roughly 2.6 million years ago, a blink in cosmic terms. But here's where it gets weird. The energy required to inflate these bubbles is staggering, equivalent to 100,000 supernovae. Could a single black hole meal really pack that much punch? Then there's the dark matter angle. Some theorists argue these bubbles might be the aftermath of dark matter particles, those elusive, invisible cosmic ghosts annihilating each other near the Galactic Center. It's a tantalizing idea because if true, these bubbles could be our first glimpse of dark matter's hidden interactions, but proving it, that's another story. The bubble's symmetrical shape defies simple explanations, their edges razor-sharp as if sculpted by forces we don't yet understand. And just when you think the mystery can't get deeper, astronomers found something inside the bubbles, a spiderweb of X-ray filaments crackling with magnetic energy. Are these cosmic power lines remnants of ancient magnetic storms, or something even stranger? Every new observation peels back another layer, revealing how little we truly grasp about the forces shaping our own galaxy. The Fermi Bubbles aren't just a scientific puzzle, they're a blazing reminder that even in our own cosmic neighborhood, the universe keeps its most explosive secrets close. Now we come to a cosmic oddity that hits closer to home. The KBC Void, the controversial local hole where the Milky Way just happens to reside. Picture our galaxy floating in a sparse bubble 7 times emptier than the rest of the universe, surrounded by an eerie cosmic underdensity stretching over 2 billion light-years wide. It's as if we're living in the middle of a vast, invisible clearing, a statistical outlier that shouldn't exist if matter was spread evenly throughout space. This discovery shakes the very foundation of the cosmological principle, the long-held assumption that the universe looks roughly the same everywhere when viewed on large enough scales. If true, the KBC Void suggests we're living in a special place, exactly what modern cosmology tries to avoid. Some researchers argue it's just a fluke, a random dip in the cosmic density that happened to form around us. But others see something deeper. The void's sheer size and our position near its center seem too precise to be coincidence. Could this underdensity be warping our measurements of the universe's expansion rate, throwing the infamous Hubble tension into sharper relief? Here's where things get thorny. When astronomers calculate how fast the universe is expanding, they get different answers depending on whether they study nearby supernova or the cosmic microwave background. The KBC Void might be skewing local measurements. If we're sitting in a giant cosmic sinkhole, the gravitational pull of surrounding dense regions could be accelerating galaxies near us, making the expansion rate seem faster than it truly is. It's like trying to measure ocean currents while drifting in a whirlpool. Your local environment distorts the bigger picture, yet not everyone's convinced. Critics point out that such a massive void should leave fingerprints in the cosmic microwave background, subtle temperature dips we haven't clearly observed. And if the void exists, why don't other galaxies show similar peculiar velocities? The debate rages on, with each new galaxy survey either fueling the fire or dousing the flames. One thing's certain, if the KBC Void is real, it's rewriting the rules of our cosmic neighborhood, forcing us to question whether we've misread the universe's grand story from our unusual front row seat. Buckle up, because we're about to tackle one of the most mind-bending cosmic mysteries yet: dark flow. Picture this: galaxy clusters, each containing hundreds of galaxies, all streaming in the same direction at breakneck speeds, as if pulled by some invisible cosmic hand. But here's the kicker: the source of this motion lies beyond the edge of everything we can observe. It's not just strange, it's downright impossible according to our current understanding of the universe. This phenomenon first caught scientists' attention when they studied the cosmic microwave background, the afterglow of the Big Bang. Tiny temperature variations in this ancient light revealed something astonishing. Entire superclusters of galaxies were moving toward a single point in space, as if drawn by a gravitational force we can't see. The numbers are staggering. These clusters are racing at nearly 2 million miles per hour toward something outside our cosmic horizon. So what could possibly exert such a pull? One radical explanation suggests the gravitational influence of another universe, a neighboring bubble in a vast multiverse, tugging on our own like a magnet hidden behind a curtain. Imagine two soap bubbles barely touching. The gravity from one could subtly distort the other without ever being directly visible. That's the multiverse theory in a nutshell. But skeptics argue this is a bridge too far. Maybe dark flow is just an artifact of incomplete data or an unknown local effect. Then there's the pre-Big Bang angle. Some theorists propose that these flows might be echoes of structures that existed before our universe began, cosmic scars left over from an earlier epoch. If true, dark flow could be our first glimpse into a reality that predates time itself. Yet for all its intrigue, dark flow remains hotly debated. Newer studies suggest the signal might be weaker than initially thought, leaving scientists divided. But one thing's certain: if confirmed, this phenomenon would upend cosmology as we know it, forcing us to rewrite the rules of gravity, the universe, and perhaps even reality itself. The idea that something beyond our universe could reach in and move entire galaxies is both terrifying and exhilarating, a reminder that the cosmos still holds cards it hasn't shown us. Deep in the cosmic microwave background, the oldest light in the universe, lies a chilling anomaly that shouldn't exist: the CMB Cold Spot. This eerie patch of sky, spanning nearly 1 billion light-years in the constellation Eridanus, registers significantly colder than its surroundings, as if a cosmic freezer door swung open in deep space. At first glance, it might seem like a glitch, a blip in the data, but the numbers don't lie. The odds of such a cold region forming randomly, less than 1 in 50. So what's sucking the heat out of this corner of the universe? Enter the Eridanus Supervoid, a staggering cosmic emptiness stretching 500 million light-years wide. This vast nothingness sits almost perfectly aligned with the cold spot, leading scientists to wonder, could the void be casting a shadow across the cosmos? Here's how it might work. As light travels through a void, it loses energy climbing out of the gravitational well, a phenomenon called the integrated Sachs-Wolf effect. Think of it like a photon running uphill, exhausted by the time it reaches us, but there's a problem. The Eridanus Supervoid, as massive as it is, shouldn't be nearly big enough to create such an extreme temperature drop. It's like trying to explain a glacier with a single ice cube. That's where the theories get wild. One possibility, the cold spot might be evidence of a cosmic defect, a texture in space-time left over from the universe's violent infancy. Imagine the early cosmos as a boiling pot of water cooling into ice. Cracks and bubbles could have frozen into the fabric of reality itself. These defects would warp space-time so severely that light passing through them would emerge fundamentally altered, creating cold spots in the CMB. Then there's the multiverse angle. Some theorists propose the cold spot could be a bruise from a collision with another universe, a parallel bubble brushing against ours in the unseen dimensions of string theory. The idea sounds like pure science fiction, but the math holds up. If true, this faint chill in the CMB might be our first evidence of realities beyond our own. Yet not everyone's convinced. Skeptics argue the cold spot could simply be instrumental noise amplified by statistical flukes. After all, when you're mapping the entire sky, anomalies are bound to pop up. But here's the twist. Newer observations reveal the Eridanus Supervoid isn't just empty, it's littered with strangely spaced galaxy clusters, as if something carved out the matter in precise, unnatural strokes. Whether it's a remnant of creation, a window to another universe, or just a cosmic mirage, the cold spot and its void remain one of the most tantalizing and frustrating enigmas in modern cosmology. One thing's clear, the universe loves keeping its biggest secrets just out of reach. Buried beneath thick veils of cosmic dust and swirling radiation, the heart of our galaxy pulses with secrets we can barely glimpse. The Milky Way's core is a place of extremes, a maelstrom of supercharged particles, violent magnetic fields, and gravitational forces so intense they twist the fabric of spacetime itself. At the center of it all lurks Sagittarius A, the supermassive black hole anchoring our galaxy. Its presence felt more than seen, despite being just 26,000 light-years away, practically a stone's throw in cosmic terms. Studying this region is like trying to decipher a message written in smoke. The challenge: imagine staring into a sandstorm while someone shines a spotlight directly in your eyes. That's what astronomers face when observing the Galactic Center. The sheer volume of dust and gas between us and Sagittarius A absorbs nearly all visible light, forcing scientists to rely on other wavelengths, infrared, X-rays, radio waves, to pierce the chaos. Even then, the view is fragmented, like reconstructing a symphony from a few scattered notes, and the radiation, it's so intense that any probe venturing too close would have its electronics fried in seconds, leaving us to study this realm from a cautious distance. Yet what we've uncovered is staggering. Sagittarius A may appear dormant now, but evidence suggests it was once a raging monster. Ancient light echoes trapped in surrounding gas clouds reveal violent outbursts, flares so powerful they sterilized entire swaths of the galaxy millions of years ago. Then there are the mysterious G objects, gas clouds masquerading as stars, stretching and contorting as they orbit the black hole like cosmic taffy. Are these the remnants of shredded planets? Or something even stranger, The Galactic Center also defies expectations with its population of young stars, crammed impossibly close to Sagittarius A star. By all rights, the black hole's tidal forces should prevent star formation entirely, yet here they are, glowing defiantly in the darkness. Some theories suggest these stars formed farther out and migrated inward, locked in a gravitational dance. Others propose they were born in the chaos itself, emerging from dense disks of gas that somehow resisted annihilation. But the biggest enigma might be the Fermi Bubbles we discussed earlier, those colossal gamma-ray structures towering above and below the core. Their symmetry hints at a connection to Sagittarius A star's past eruptions, yet the energy required staggers the imagination. Was this a single cataclysmic event or the cumulative effect of smaller bursts? And lurking beneath it all, dark matter. The Galactic Center's gravitational quirks suggest an invisible halo of this mysterious substance might be fueling the chaos, its presence felt but never seen. Every breakthrough here raises new questions. Why does Sagittarius A star flare unpredictably, brightening by factors of hundreds in minutes? What creates the bizarre, magnetized filaments crisscrossing the core like cosmic spiderwebs? And could the extreme physics at play here hold clues to unifying Einstein's relativity with quantum mechanics? The Galactic Center isn't just a scientific puzzle, it's a front-row seat to the universe's most violent and beautiful forces, a place where the rules we know bend, break, and sometimes rewrite themselves entirely. And until we find a way to peer deeper through the dust, its greatest secrets will remain locked away, pulsing in the dark. The far side of the moon, our celestial neighbor's hidden face, has fascinated humanity for centuries. Though it orbits just 239,000 miles away, this rugged lunar wilderness might as well be on the other side of the universe when it comes to exploration. Unlike the familiar craters and man-in-the-moon patterns we see from Earth, the far side is a world apart, sculpted by ancient impacts and volcanic forces into a landscape so alien it might as well belong to another planet. One of the biggest barriers to unlocking its secrets is simple geometry. The moon is tidally locked, meaning it rotates at the same rate it orbits Earth, forever keeping one hemisphere pointed away from us. Without a direct line of sight, radio signals can't penetrate, creating a communication blackout so absolute that even orbiters lose contact when circling behind it. To bridge this gap, missions like China's Chang'e 4 rely on relay satellites, bouncing signals off an intermediary spacecraft just to whisper commands to its lunar rover. It's like trying to FaceTime someone from a cave with no service, except the cave is a cratered wasteland 200,000 miles deep in space. Then there's the terrain itself. The far side lacks the vast, smooth Maria dark plains of ancient lava that dominate the near side. Instead, it's a craggy jumble of impact basins like the South Pole Aitken Basin, one of the solar system's oldest and deepest scars, stretching 1,500 miles wide and plunging miles into the lunar crust. Samples from this region could rewrite our understanding of the moon's violent infancy, preserving material from a time when the inner solar system was a shooting gallery of colliding protoplanets. But landing here is a nightmare without flat plains. Even robotic missions risk toppling into jagged highlands or shadowed pits. And of course, no discussion of the far side would be complete without addressing the myths. Conspiracy theories about alien structures or secret bases have swirled since the Soviet Luna 3 first photographed its battered surface in 1959. The truth, the far side's isolation makes it an ideal spot for radio astronomy free from Earth's electromagnetic noise, leading to legitimate projects like China's low-frequency radio telescope. But the lack of atmospheric interference also amplifies echoes and static, creating radio anomalies easily misinterpreted by eager UFO hunters. Yet the real treasure here isn't aliens, it's science. The far side's pristine silence could reveal whispers from the universe's dawn, like faint signals from the cosmic dark ages before stars ignited. Its battered highlands might hide clues to how Earth itself formed. And let's not forget the potential for future lunar bases shielded from our planet's radio chatter. The far side isn't just a barren backwater. It's a time capsule, a telescope, and maybe even humanity's next frontier. If only we could figure out how to talk to it. Beyond the last whispers of Neptune's orbit, far past the scattered debris of the Kuiper belt, lies a frigid frontier so vast it defies comprehension, the Oort cloud. This hypothetical shell of icy remnants stretches nearly a light year from the Sun, a distance so enormous it makes Pluto's orbit look like a backyard stroll. Imagine every comet you've ever seen streaking across the night sky. They likely began their journey here, in this frozen graveyard of the solar system's infancy. Yet for all its significance, the Oort cloud remains the ultimate cosmic tease, a realm we know must exist but can't directly observe, let alone explore. Why is this distant halo so elusive? For starters, the objects lurking here are practically invisible. Unlike the rocky asteroids of the inner solar system or even the dwarf planets of the Kuiper belt, Oort cloud denizens are primordial icebergs, dark, fragile clumps of ice and dust, some no larger than a city block. At these distances, sunlight is a faint candle, offering no warmth or illumination to reflect back to our telescopes. Even Hubble strains to spot them, catching only fleeting glimpses when one gets nudged inward, transforming into a comet with a glowing tail. Then there's the sheer scale. The inner edge of the Oort cloud might begin around 2,000 astronomical units from the Sun. That's 2,000 times farther than Earth. But its outer reaches could extend to 100,000 O, brushing against the gravitational influence of neighboring stars. To put that in perspective, Voyager 1, humanity's farthest flung probe, has traveled just over 150 O in 46 years. At its current speed, reaching the Oort cloud's doorstep would take another 300 centuries. It's the ultimate reminder that some frontiers remain stubbornly out of reach, no matter our ambition. Yet the Oort cloud's remoteness hides a paradoxical truth. It's the solar system's silent architect. Long-period comets like Hale-Bopp, which dazzled Earth in 1997, are cosmic messengers from this frozen fringe, hurled toward us by passing stars or galactic tides. These icy time capsules preserve chemistry from the solar system's birth, untouched by heat or radiation for 4.5 billion years. Some might even carry ingredients critical to life, organic molecules or water, hinting that the Oort cloud could have seeded Earth's oceans during the chaotic early days of planetary formation. And here's where it gets stranger. The Oort cloud might not belong to us at all. Simulations suggest up to 90% of its objects could be interstellar interlopers, captured from other star systems during the Sun's wild youth in a dense stellar nursery. If true, this means the outer solar system is a museum of stolen ice, a gallery of frozen artifacts from across the galaxy. For now, the Oort cloud lingers in the realm of theory, its existence inferred from the graceful arcs of comets rather than direct observation. But new telescopes like the Vera Rubin Observatory might finally spot its sedately drifting inhabitants, while missions like the proposed interstellar probe aim to chart its boundaries. Until then, this distant, icy veil remains one of the solar system's last great mysteries, a reminder that even in our own cosmic backyard, the universe keeps its coldest, oldest secrets locked away. The heliopause is the solar system's final frontier, a shifting, invisible boundary where the Sun's influence falters and the void of interstellar space takes over. Picture our star as a cosmic lighthouse, constantly flinging out charged particles in all directions, the solar wind. This wind carves out a protective bubble around the entire solar system, shielding us from harsh galactic radiation like an invisible force field. But out where the solar wind weakens, slamming into the cold, dense plasma of interstellar space, the two clash in a turbulent zone of magnetic chaos. This is the heliopause, a place where the rules of physics as we know them start to unravel. For decades, this boundary existed only in theory until the Voyager probes became the first human-made objects to cross it. Voyager 1 breached the heliopause in 2012, followed by Voyager 2 in 2018. Their readings shocked scientists. Instead of a clean, defined border, the probes encountered a messy, frothy transition layer where magnetic fields tangle and interstellar particles backwash into our solar system like seawater seeping into a boat. Even more bizarre, the heliopause appears to be moving, expanding and contracting like a lung with the Sun's 11-year activity cycle. But here's the kicker: the Voyagers barely scratched the surface of this region's mysteries. Their instruments, designed in the 1970s, weren't equipped to fully analyze the plasma environment, leading to gaps in our understanding. For instance, why did Voyager 1 detect a sudden drop in solar particles while Voyager 2, just a few years later, recorded a gradual tapering? Was this a quirk of their different trajectories, or evidence that the heliopause behaves differently in different directions? Then there's the matter of the hydrogen wall, a mysterious band of dense hydrogen gas piled up just beyond the heliopause detected by NASA's New Horizons probe. Some theorize this wall could be interstellar material slowing down as it presses against our solar bubble. Others suggest it might be the fingerprints of an ancient supernova, its shock waves still rippling through our galactic neighborhood. And perhaps the biggest enigma: what happens to cosmic rays here? The heliopause was thought to act as a filter, softening the barrage of high-energy particles from deep space. But Voyager's data revealed unexpected spikes in radiation, hinting at complex magnetic interactions we can't yet model. It's as if the heliopause isn't just a barrier, it's an active participant in a cosmic tug-of-war, reshaping particles as they pass through. The implications go far beyond curiosity. Understanding this region could revolutionize how we plan future interstellar missions. Without the Sun's protection, radiation levels skyrocket, a serious hazard for astronauts or electronics. Plus, the heliopause might hold clues to how other stars interact with their own interstellar surroundings, offering a universal template for how solar systems breathe in the galactic wind. Yet for all we've learned, the heliopause remains a realm of unanswered questions. Is it porous, letting interstellar material seep in? Why do its magnetic fields fluctuate unpredictably? And how does it influence the shape of the solar system's tail? Yes, the Sun drags a comet-like wake through the galaxy, and nobody knows exactly how it behaves out here. Until we send newer, more advanced probes to this distant shore, the heliopause will keep its secrets, a magnetic maze at the edge of everything we call home. Fast radio bursts are the universe's most enigmatic Morse code, blaring signals that vanish as quickly as they appear, leaving astronomers scrambling for answers. These bursts pack more energy in a millisecond than the Sun emits in 3 days, yet their sources remain ghostly, flickering across the cosmos without warning. Some erupt just once, while others repeat in erratic patterns, like a cosmic alarm clock set to no discernible rhythm. The strangest part, we've detected hundreds of these bursts since their discovery in 2007, tracing them to galaxies billions of light-years away, but pinpointing what's causing them. That's where the real mystery begins. Take FRB 1218, a repeater located in a dwarf galaxy 3 billion light-years distant. Its signal arrives with a telltale twist. The radio waves spiral like a corkscrew, a phenomenon suggesting they've traveled through an intensely magnetized environment. The prime suspect, a magnetar, a type of neutron star with a magnetic field 1 trillion times stronger than Earth's. These cosmic powerhouses could unleash bursts when their crusts crack under magnetic strain, like a planetary-scale earthquake rippling with energy. Yet even this explanation has holes. Why do some bursts repeat while others don't? And how could a single magnetar produce flares as energetic as FRB 2020, which released enough power in milliseconds to rival Earth's entire energy consumption for centuries? Then there's the collision theory. When two neutron stars spiral into each other, their merger could unleash a cataclysmic burst of energy, a one-time cosmic firework. This fits non-repeating FRBs, but fails to explain why we've detected some bursts from the same location years apart. Could a neutron star collision leave behind a remnant capable of firing off multiple signals? Or are we seeing something far stranger, like cosmic strings, hypothetical defects in spacetime left over from the Big Bang? These ultra-dense rips in the universe's fabric could vibrate like plucked guitar strings, emitting bursts as they snap. And yes, the alien hypothesis lingers. The signal's brevity and intensity mirror what we might expect from artificial beacons, interstellar lasers, or propulsion systems harnessing unimaginable energy. SETI researchers have even scanned repeating FRBs for patterns, though no evidence of encoding has surfaced. Still, the possibility tantalizes. What if these bursts are cosmic lighthouses, built by civilizations advanced enough to harness the power of stars? The truth is, FRBs remain frustratingly out of reach because of their sheer unpredictability. By the time telescopes swing toward a burst's origin, it's already faded, leaving only a faint afterglow of questions. New facilities like the CHIME array in Canada are revolutionizing the hunt, detecting dozens of bursts monthly, but without catching one in the act from a known source. Like a magnetar flaring in our own galaxy, theories will keep multiplying. What's clear is this: every burst is a message bottled in the deep ocean of space, carrying clues about the universe's most extreme environments. Whether they're born from dying stars, space-time defects, or something beyond our imagination, FRBs remind us that the cosmos still speaks in riddles, and we're only just learning to listen. The Milky Way, our glittering home galaxy, holds an ironic secret. It's hiding a staggering 20% of the observable universe behind its own shimmering veil. This is the zone of avoidance, a thick band of cosmic dust, gas, and starlight so dense it blots out entire galaxies like a celestial blindfold. Imagine trying to study a painting while standing behind a spotlight. The glare obscures everything behind it. That's the challenge astronomers face when they point telescopes toward our galaxy's plane. But why does this zone matter? Because beyond its murky curtain could lie answers to some of cosmology's biggest puzzles: unseen galaxy clusters, hidden gravitational forces, even clues to the universe's lopsided structure. Early sky surveys revealed a glaring asymmetry. Galaxies seem to avoid the Milky Way's plane entirely, not because they weren't there, but because their light couldn't penetrate the chaos. The first attempts to explore this void were like mapping a city by listening to muffled voices through a wall, frustratingly indirect. Then came the game changers: infrared and radio astronomy. Infrared light slips through dust like warmth through a winter glove, revealing galaxies otherwise invisible. Projects like NASA's WISE telescope have peeled back the layers, uncovering thousands of hidden galaxies lurking in the zone's shadows. Radio waves, meanwhile, cut through the interference entirely, exposing structures like the mysterious Norma cluster, a colossal gathering of galaxies hidden right behind our own galactic center, its gravity warping spacetime in ways we're only beginning to measure. Yet the surprises don't stop there. Some of these obscured galaxies appear to be racing toward an unseen attractor, fueling speculation that the zone hides more than just galaxies, perhaps even another Great Attractor-style anomaly. Others show bizarre distortions, their shapes stretched by dark matter's invisible hand. And then there's the Vela supercluster, a recently discovered behemoth stretching 500 million light-years, its full extent still obscured by our own galaxy's bulk. What makes the zone of avoidance so tantalizing is its dual nature: a cosmic blind spot and a treasure trove rolled into one. Every new wavelength we use to probe it, from X-rays to neutral hydrogen mapping, reveals another piece of the puzzle. Some researchers believe the missing mass concealed here could help solve the missing baryon problem, where half the universe's ordinary matter remains unaccounted for. Others wonder if undiscovered dwarf galaxies, relics from the universe's infancy, might be hiding in plain sight. The irony is poetic. We've sent probes to the edges of the solar system and glimpsed galaxies billions of light years away, yet a slice of the cosmos practically next door remains wrapped in mystery. The zone of avoidance isn't just a technical hurdle, it's a reminder that sometimes the biggest discoveries are hidden right where we least expect to look. And with next-generation telescopes like the Square Kilometre Array poised to scan this region in unprecedented detail, we might soon lift the Milky Way's veil for good. The Hubble volume represents the ultimate cosmic horizon, the farthest we could ever hope to see, even with the most powerful telescopes imaginable. Picture standing in the middle of an endless, expanding balloon, where every point on its surface is racing away from you faster and faster. At some distance, galaxies are receding so quickly that their light can never reach us, no matter how long we wait. This invisible boundary defines the edge of our observable universe, a sphere roughly 93 billion light-years across, encapsulating every star, galaxy, and photon visible from Earth. But here's the unsettling truth. The Hubble volume isn't fixed, it's shrinking. Not because the universe is contracting far from it, but because the expansion of space is accelerating. Dark energy, that mysterious force driving galaxies apart, is pushing the cosmic horizon inward over time, like waves overtaking a swimmer struggling toward shore. Already, countless galaxies once within our view have vanished beyond this horizon, their light stretched into oblivion by the relentless stretching of space-time. Future astronomers may never know they existed, so what lies beyond this boundary? The answer depends on who you ask. Some theories suggest more of the same. An infinite sprawl of galaxies, stars, and planets extending forever, just forever out of reach. Others propose a far stranger possibility: bubble universes. Imagine a cosmic foam where each bubble is a self-contained universe with its own laws of physics, inflation rates, and even dimensions. Our Hubble volume might just be one tiny pocket in this multiverse, completely isolated from neighboring realities where gravity repels or time runs backward. The scariest part we'll likely never know for sure. Then there's the holographic principle, a mind-bending idea that the Hubble volume's boundary isn't just a limit, it's a screen. Some physicists argue that all the information within our observable universe could be encoded on this surface like a cosmic projection. If true, everything we experience, stars, planets, even our own thoughts, might just be shadows cast from the edge of reality. But perhaps the most humbling thought is this: even within our observable universe, we're seeing only a fraction of what's out there. Light from the most distant galaxies hasn't reached us yet, and some never will. The Hubble volume is less a window and more a keyhole, a fleeting glimpse into a cosmos vaster and stranger than we dare imagine. The Virgo supercluster is our cosmic neighborhood, a sprawling web of galaxies stretching over 100 million light-years, with the Milky Way as just one speck among thousands. But even here, at the edges of our local supercluster, the universe throws curveballs that force us to question everything we think we know. Beyond the familiar galaxies of Virgo and Hydra lies a frontier where the cosmic map dissolves into uncertainty, where vast structures loom in the darkness, defying our models of how the universe should be arranged. Take the so-called Southern Wall, a recently discovered filament of galaxies arcing across the southern sky. This immense structure, spanning at least 500 million light-years, appears to be part of an even larger network, one that shouldn't exist according to standard cosmology. Simulations of the universe's evolution predict matter should be distributed fairly evenly on the largest scales. Yet here we are, staring at a galactic freeway that dwarfs even the famed Sloan Great Wall. How does something this colossal form without disrupting the delicate balance of cosmic expansion? Some theorists suggest dark matter's invisible scaffolding might be knitting these walls together in ways we don't yet understand, while others wonder if we're seeing the imprint of primordial gravitational waves frozen into the universe's fabric during the Big Bang. Then there's the opposite problem, voids. Beyond the Virgo supercluster's edge, astronomers have spotted gaping holes in the galactic tapestry regions so empty they make the Boots void look like a crowded subway. One such void, dubbed the local mini-hole, stretches nearly 200 million light-years across, its near-total lack of galaxies challenging our understanding of how matter clumps together over time. If voids this size are common, they could skew our measurements of the universe's expansion rate, throwing the Hubble tension into even sharper relief. But the real enigma, something's tugging at us, the Milky Way, along with hundreds of other galaxies in our supercluster, is drifting toward an unseen gravitational anchor beyond Virgo's edge, an effect cosmologists call dark flow. This motion suggests there's far more mass lurking in the darkness than our telescopes can detect, perhaps in the form of superclusters so distant their light hasn't reached us yet. Or worse, what if the Virgo supercluster itself is just a small branch of something incomprehensibly larger, like the Laniakea supercluster, which spans 500 million light-years? Recent studies hint that even Laniakea might be a minor suburb of an even grander structure, a cosmic continent whose full shape remains hidden behind the curtain of the observable universe. This raises a haunting possibility. What if our entire corner of space, from the Milky Way to the farthest reaches of Virgo, is just a backwater in a universe far more complex and interconnected than we've dared to imagine? Every time we think we've grasped the scale of things, the cosmos reveals another layer, another tier of structure that forces us to redraw the maps. The edge of the Virgo supercluster isn't just a boundary, it's a mirror, reflecting how much we still don't know about the universe we call home. Even the Big Bang wasn't the beginning, at least not the way we imagine it. Rewind the universe far enough, and you'll hit a wall where time itself loses meaning. The Planck era, the first incomprehensibly tiny fraction of a second after everything began. We're talking 10 to the power of negative 43 seconds, a timescale so brief it makes the blink of an eye seem eternal. In this fleeting instant, the cosmos wasn't just hot or dense. It existed in a state so extreme that the very laws of physics as we know them didn't just bend, they shattered entirely. Picture this, temperatures soaring beyond 10 to the power of 32 degrees, energy so intense that gravity, typically the weakest of forces, suddenly became as powerful as electromagnetism or the nuclear forces. Under these conditions, spacetime itself would have been a seething quantum foam, bubbling with virtual black holes that popped in and out of existence like bubbles in boiling water. Matter and energy wouldn't have behaved as particles or waves. They'd have been something far stranger, flickering in and out of dimensions we can't even perceive. It's a realm where here and now cease to have clear definitions, where the universe was smaller than a single atom yet contained the seeds of everything we see today. And here's the frustrating part. We know this epoch must have existed, but it's utterly unreachable with our current tools. Why? Because to probe the Planck era, we'd need a theory that unites quantum mechanics with general relativity, a so-called theory of quantum gravity. Einstein's equations crumble at these energy scales, predicting infinite densities that make no physical sense. Meanwhile, quantum physics, which excels at describing the subatomic world, has no language for gravity's curvature of spacetime. It's like trying to use a recipe for baking cookies to build a skyscraper. The ingredients just don't translate. String theory offers one possible glimpse beyond the veil, proposing that particles aren't dots but vibrating strings whose harmonies dictate the laws of physics. In this framework, the Planck era might have been a symphony of higher dimensional vibrations, a cosmic dance we can't yet hear. Loop quantum gravity, another contender, suggests spacetime itself is woven from tiny, indivisible loops, a pixelated reality where the Planck era marks the smallest possible frame of existence. Yet neither theory has produced testable predictions, leaving us with mathematical elegance but no way to peek into the cosmic dawn. Even our mightiest particle colliders are powerless here. The Large Hadron Collider smashes protons at energies a trillion times too weak to recreate Planck-scale conditions. To reach those energies, we'd need an accelerator the size of the Milky Way, or a way to harness the mind-bending power of cosmic inflation's relics. Some scientists hunt for imprints of the Planck era in the cosmic microwave background, searching for faint swirls that might hint at quantum gravity's fingerprints. Others listen for the echoes of primordial black holes evaporating into Hawking radiation, their deaths carrying whispers of spacetime's quantum nature. The Planck era isn't just a scientific frontier, it's a philosophical challenge. If we can't observe it directly, how do we know anything about it? Some argue it's a boundary beyond which science can't pass, a curtain the universe has drawn over its own origins. Others see it as the ultimate puzzle, daring us to invent new mathematics, new experiments, perhaps even new ways of thinking. One thing's certain, until we crack quantum gravity, the first moments of existence will remain locked away, a cosmic vault with no key in sight, a reminder that some mysteries are written in energies too fierce for even light to survive. At the heart of every black hole lies a cosmic paradox so profound it threatens to unravel our understanding of reality itself, the singularity. This is the point where all known laws of physics collapse, where matter is crushed into infinite density, and where space-time curves so sharply it effectively ceases to exist. But here's the twist: we'll never see it. Not because it's too far away or too small, but because the universe itself seems to have declared it off limits, hidden behind an impenetrable curtain called the event horizon. Physicists call this idea cosmic censorship, nature's way of shielding us from the chaos lurking in the darkness. Think of the event horizon as a one-way mirror. Light, matter, even information can cross inward, but nothing escapes. That means every black hole's singularity is eternally veiled, its secrets locked away where no telescope or probe can reach. But why should the universe care what we see? Because without this cosmic censorship, the unpredictability of a naked singularity, one exposed to the outside universe, could wreak havoc on causality itself. Imagine a place where gravity spirals into infinite strength without warning, where time stutters and skips like a broken record. The very fabric of reality would become unstable, making the future impossible to predict. This leads to one of the fiercest debates in theoretical physics. Is information truly lost when it falls into a black hole? On one side, Stephen Hawking famously argued that black holes evaporate over time, slowly leaking energy in the form of Hawking radiation, and with it any trace of what fell in. This information paradox suggests the universe has a serious memory problem, violating quantum mechanics' core tenet that information can never be destroyed. On the other side, rebels like Leonard Susskind proposed the holographic principle, the idea that every bit of information swallowed by a black hole is somehow encoded on its event horizon like a cosmic hard drive. If true, the singularity isn't a cosmic shredder, it's more like a vault, its contents preserved in a form we don't yet understand. But what if there's a back door? Enter wormholes, hypothetical tunnels through space-time that could, in theory, connect the singularity to another point in the universe or another universe entirely. Einstein's equations allow for such bridges, though they'd require exotic matter with negative energy to stay open. If wormholes exist, they might offer a way to peek behind the cosmic censorship curtain without breaking physics, a loophole where information slips through unharmed. Some models even suggest that black holes are wormholes, their singularities gateways rather than dead ends. Of course, this is all speculation. No one knows what truly happens beyond the event horizon, and without a way to test these ideas, the singularity remains the ultimate locked room mystery. But that hasn't stopped physicists from dreaming up wild scenarios. Could advanced civilizations harness singularities as quantum computers, tapping into their infinite density for computation? Or are they cosmic recycling centers, crushing matter into its primordial state before spewing it back out as new universes in a big bang like rebirth? The cosmic censorship zone isn't just about hiding singularities, it's about preserving the rules that make science possible. If nature didn't shield us from these infinite anomalies, the universe would be a far stranger, far less predictable place. Yet the irony is delicious. In trying to protect us from chaos, the universe has created one of its most tantalizing enigmas. Somewhere beyond the reach of light or logic, the singularity waits, a riddle wrapped in a horizon hidden in the heart of darkness. Around every galaxy, including our own Milky Way, swirls a ghostly enigma. The dark matter halo, an invisible cocoon of mass that holds the cosmos together. Unlike black holes or neutron stars, this mysterious substance doesn't absorb or emit light. It doesn't even interact with ordinary matter except through gravity. Yet without it, galaxies would fly apart, their stars scattering like marbles dropped on a highway. Picture spinning a bucket of water on a rope. If the bucket were a galaxy, the rope is the dark matter halo, its unseen grip keeping everything from spiraling into chaos. So what is this elusive stuff? The leading candidates sound like something from a physicist's fantasy novel, WIMP and actions. WIMP, weakly interacting massive particles, are hypothetical heavy particles that barely talk to normal matter, passing through entire planets like shadows through glass. Actions, on the other hand, are ultra-lightweight particles, possibly 1 trillion times lighter than electrons, flitting through space like cosmic whispers. Both should be everywhere, yet after decades of hunting with detectors buried deep underground or suspended in space, we've caught exactly nothing. The frustration is palpable. Experiments like the Large Underground Xenon Lux detector and the Action Dark Matter experiment ADMX have turned up empty-handed, pushing scientists to rethink their assumptions. Maybe dark matter isn't a single particle but a spectrum, a family of oddballs we haven't even imagined yet. Or perhaps it's not particles at all, but primordial black holes formed in the universe's first second, lurking unseen. Some theorists even suggest modifications to gravity itself, arguing that Newton and Einstein might have missed something fundamental about how mass bends spacetime on galactic scales. Yet the evidence for dark matter's existence is overwhelming. Watch a galaxy rotate. Stars on the outer edges move just as fast as those near the center, defying the laws of gravity unless there's something extra tugging on them, something invisible. Or peer at colliding galaxy clusters like the Bullet Cluster, where the visible gas smashes together while the mass, traced by gravitational lensing, glides right through as if it didn't notice the crash. Here's the kicker: even if we never directly detect dark matter, its influence is written across the cosmos. It shaped the universe's large-scale structure, acting as a cosmic scaffold that guided galaxies into their grand designs. It might even determine the universe's ultimate fate, whether expansion slows, halts, or tears everything apart. The hunt continues with new detectors like the upcoming LUX Zeppelin experiment and space telescopes like Euclid poised to scan the heavens for dark matter's faint fingerprints. Will we ever see it? Maybe not in the traditional sense, but like the wind-shaping dunes or electricity powering cities, dark matter's presence is undeniable, even if it forever eludes our grasp. Until then, it remains the universe's most pervasive ghost, an invisible architect silently holding the stars in place. Travel back 12 billion years to an era when the universe was a cosmic Wild West, a time when quasars ruled the skies. These blazing beacons, the brightest objects in existence, outshone entire galaxies with light equivalent to 1 trillion suns. But for all their brilliance, quasars are cosmic magicians, masterful at dazzling us while keeping their secrets locked away. The very qualities that make them visible across the universe also conspire to hide their true nature, leaving astronomers to piece together clues from the glare. At the heart of every quasar lies a supermassive black hole, gorging on gas and dust at a rate that defies imagination. Picture a whirlpool of matter, spiraling inward at nearly the speed of light, heating up to millions of degrees before vanishing beyond the event horizon. The energy released in this frenzy powers jets of plasma that shoot outward for thousands of light years, lighting up intergalactic space like celestial lighthouses. Yet here's the paradox: that same brilliance drowns out the details. The glare from the quasar's core is so intense it washes out the faint glow of its host galaxy, leaving us blind to the environment that birthed these monsters. Distance adds another layer of frustration. The most energetic quasars exist in the early universe, so far away their light has traveled for eons to reach us. By the time it arrives, stretched and redshifted by cosmic expansion, key details are lost in the noise. It's like trying to study a fireworks display through frosted glass. You see the explosion but miss the mechanics behind it. Even the Hubble Space Telescope strains to resolve their host galaxies, catching only ghostly hints of the structures that should, in theory, surround them. But the greatest mystery lies in their central engines. How did black holes grow so massive, so fast? Some quasars existed when the universe was less than 1 billion years old, too young, by conventional models, for black holes to bulk up to billions of solar masses. One theory suggests they feasted on streams of cold gas flowing through the cosmic web, gorging in an era when the universe was denser and richer in fuel. Others propose they were born big, collapsing directly from primordial gas clouds into heavyweight champions, skipping the usual growth spurts. Then there's the puzzle of their on-off switch. Quasars don't burn forever. They flicker to life and fade as their fuel runs out. But what sparks them awake and what puts them back to sleep? Some might be triggered by galaxy collisions, which funnel fresh gas toward the black hole like logs tossed on a fire. Others could awaken more quietly as instabilities in their host galaxies disrupt orbiting gas clouds, sending them spiraling inward. New instruments like the James Webb Space Telescope are finally peeling back the glare, revealing the galaxies hidden beneath the quasar's brilliance. Early images show chaotic, misshapen host galaxies still under construction, their stars forming in furious bursts. Meanwhile, radio telescopes like ALMA have caught quasars in the act of rearranging their surroundings, their jets carving bubbles in interstellar gas like a blowtorch through wax. Yet for all our progress, the quasar era remains a tantalizing enigma. These cosmic lighthouses guided the universe through its turbulent youth, their light a beacon across time. But their full story, that's still written in shadows, waiting for the next breakthrough to bring it into focus. Imagine the universe waking up, not with a bang, but with a slow, flickering glow. This is the reionization epoch, a cosmic dawn stretching from about 100 million to 1 billion years after the Big Bang, when the first stars and galaxies ignited, burning away the fog of neutral hydrogen that had shrouded the cosmos since its birth. These pioneer stars didn't just light up the darkness, they fundamentally rewrote the rules of the universe, blasting it with enough ultraviolet radiation to rip electrons from hydrogen atoms in a process called reionization. The entire cosmos became transparent for the first time, transforming from a murky void into the star-filled expanse we know today. Yet observing this pivotal era is like trying to watch a sunrise through a thunderstorm. The light from these first stars is astonishingly faint, stretched by cosmic expansion into infrared wavelengths that slip through most telescopes like ghosts. Worse, the very hydrogen these stars ionized now acts like a cosmic smokescreen while modern galaxies shine clearly through transparent space. Those early pioneers are obscured by the last wisps of the fading fog they sought to burn away. It's a cruel irony. The event that cleared the universe also hides its own fingerprints. For decades, the reionization epoch existed only in theory. Then came the game changer, the cosmic microwave background. Tiny fluctuations in this ancient afterglow, mapped by missions like Planck, revealed patches where hydrogen was ionized earlier or later than average scars from the first stellar fires. Meanwhile, deep field observations from Hubble glimpsed galaxies from just after reionization's end, their light warped and magnified by gravitational lensing. These faint smudges, some over 13 billion light-years away, showed stars forming at rates 100 times faster than the Milky Way today. But the epoch's true pioneers, the stars that sparked it all, remain maddeningly out of reach. Why is this so hard? Beyond the obvious hurdles of distance and dimness, there's another problem. The first stars weren't like ours. Theorized to be monstrous blue giants hundreds of times the sun's mass, they lived fast, died young, and left behind no solar systems, only black holes and heavy elements that seeded future generations. Their ultraviolet fury would have been absorbed by nearby hydrogen, leaving no direct spectral traces. Even the James Webb Space Telescope, designed to hunt these cosmic firstborns, sees mostly their successors' galaxies that formed slightly later in a universe already partway cleared. The clues we do have are tantalizing. Quasars from this era, their light filtered through lingering hydrogen clouds, show shadowy absorption lines, gaps in their spectra where neutral hydrogen blocked specific wavelengths. These lines act like a cosmic barcode, revealing how much fog remained at different times. Meanwhile, radio astronomers chase an even fainter signal, the 21-centimeter line, a whisper from primordial hydrogen as it transitioned from neutral to ionized. Projects like the Square Kilometre Array aim to map this signal in 3D, creating a tomographic scan of the universe's adolescence, but the ultimate prize: catching a population Roman 3 star, the hypothetical first generation of stars, forged from pure hydrogen and helium. These celestial dinosaurs would lack the heavy elements that define all known stars, making them nearly invisible to conventional searches. Some theorists suggest they might be found in the Milky Way's halo, ancient refugees from smaller galaxies consumed long ago. Others propose looking for their supernova remnants, unusually pure bubbles of iron scattered in deep space. The reionization epoch isn't just a missing chapter in cosmic history, it's the moment the universe became recognizable, the bridge between formless darkness and the glittering web of galaxies we see today. And while its pioneers remain elusive, every flicker of distant light, every shadow in a quasar spectrum, brings us closer to understanding how the cosmos learned to shine. What if everything we call the universe, every galaxy, every atom, every law of physics is just one tiny bubble floating in an endless, frothing sea of other realities? This is the multiverse hypothesis, a mind-bending idea that what we see through our telescopes might be less than a fraction of what's actually out there. Imagine blowing soap bubbles in your backyard. Each floats independently, its shimmering surface separating one pocket of air from another. Now picture those bubbles as entire universes, each with its own unique physics, its own version of time, maybe even its own alien civilizations completely unaware of our existence. The math behind this isn't just science fiction. Inflation theory, our best explanation for the Big Bang's explosive growth, suggests that once space starts expanding faster than light, it never stops. Regions of spacetime could pinch off into isolated pockets, stretching beyond any possible contact with one another. Some versions of string theory take this further, proposing a landscape of possible universes, 10 to the power of 500 variations, each with different particles, forces, even dimensions. In one, gravity might be 1,000,000 times stronger. In another, atoms could never form, leaving behind a cold, dark void. But here's the catch: if other universes exist, we can't see them, talk to them, or even prove they're there. The space between bubble universes expands faster than light, putting them forever beyond our cosmic horizon. It's like standing in a pitch-black forest, knowing there are other campfires burning somewhere in the distance, but separated by miles of impenetrable night. Some theorists hunt for indirect evidence cosmic bruises where our bubble might have bumped against another during inflation, leaving faint swirls in the microwave background. Others suggest that dark flow, those mysteriously drifting galaxy clusters, could be tugged by gravity from a neighboring universe. So far, no smoking gun. The multiverse isn't just about space, it's about possibility. If infinite versions of reality exist somewhere out there, a universe identical to ours might have taken a different turn. A version where dinosaurs never went extinct, where Earth formed closer to the galactic core, or where you made that left turn instead of a right last Tuesday. It's a dizzying thought, equal parts exhilarating and unsettling. Yet for all its grandeur, the multiverse remains profoundly frustrating. By its very definition, it might always lie beyond the reach of science, more philosophy than physics. Some argue that if a theory can't be tested, it doesn't belong in science at all. Others counter that the math points us there, like a compass needle trembling toward an invisible north. Whether cosmic reality or beautiful dead end, the multiverse challenges us to ask, how much of existence is meant to be known, and how much will forever linger just beyond the edge of understanding, a shadow dancing at the corner of the universe's eye. Zoom in far enough, past atoms, past protons, past even the tiniest quarks, and space-time itself stops being smooth. Instead, it seethes. This is the quantum foam, the universe's ultimate basement level, where the fabric of reality churns with violent uncertainty at scales 100 billion times smaller than an atomic nucleus. Here, the neat grids of Einstein's spacetime dissolve into a frenzied dance of microscopic black holes and wormholes, blinking in and out of existence so fast they barely leave a trace. It's as if the cosmos is built on a foundation of bubbling champagne, fizzy, chaotic, and utterly unpredictable. Why can't we see this frothy underworld? The problem isn't just scale, it's energy. To probe the quantum foam, you'd need a microscope powered by particles with energies a quadrillion times more intense than what the Large Hadron Collider can muster, a machine the size of Jupiter's orbit. Even then, there's a cosmic catch-22. The very act of observing such tiny distances would concentrate enough energy to create a black hole right in your detector. It's like trying to study the ripples in a pond by dropping a boulder into it. You destroy the thing you're trying to measure. The quantum foam isn't just a curiosity, it's a battleground for physics itself. Einstein's relativity paints spacetime as a smooth, flexible sheet, while quantum mechanics insists everything is discrete and jittery. The foam is where these theories collide, screaming at each other in mathematical contradictions. Imagine trying to merge the rules of chess with the rules of jazz. Both are elegant, but together they're chaos. That's the crisis physicists face when they peer into the foam's depths. Some theorists believe this turbulence leaves faint fingerprints. If spacetime is foamy, light traveling across the universe might stumble on its way, like a ballerina dancing on a floor full of marbles. Over billions of light years, those tiny stumbles could add up, distorting the arrival times of gamma rays from distant explosions. NASA's Fermi telescope has hunted for this effect, but so far, space looks disappointingly smooth. Maybe the foam's bubbles are smaller than we thought, or maybe we're looking for the wrong clues. Then there's the holographic principle, a radical idea that the quantum foam's complexity might be projected from a two-dimensional surface at the edge of the universe. Picture a movie screen where every pixel encodes a point in three-dimensional space. If true, the foam's chaos isn't fundamental. It's just a shadow of deeper, stranger physics playing out in a dimension we can't perceive. For now, the quantum foam remains a realm of equations and imagination. It taunts us with questions. Is spacetime pixelated? Do wormholes really flicker in and out of existence? And if we ever could see this froth, would it redefine reality itself? Until we bridge the gap between relativity and quantum mechanics, The foam will stay hidden, a reminder that sometimes the universe's most profound secrets lie just beyond the limits of our tools and perhaps our minds. At the very beginning, before stars, before atoms, before even the concept of space, there was a moment so incomprehensible that our laws of physics simply give up. The Big Bang singularity isn't just a point in time. It's the edge of reality itself, a boundary where the universe's entire history collapses into a single, infinitely dense speck. Picture squeezing every galaxy, every planet, every particle of matter into a space smaller than a single atom, crushed to a point where gravity becomes infinite and time loses all meaning. This is where science hits a wall. The equations of general relativity, which flawlessly describe black holes and the bending of spacetime, break down entirely when asked to describe time zero. At the singularity, the math yields nonsense: infinite densities, infinite curvature, infinite everything. It's like asking a calculator to divide by zero. The machine just sputters in protest. Quantum mechanics doesn't fare much better. While it thrives on the bizarre behavior of the ultra-small, even it can't reconcile the sheer extremity of the Big Bang's starting conditions. The truth is, we lack a theory of quantum gravity, a framework that could marry these two pillars of physics, and without it, the singularity remains the ultimate dead end. This raises an even more unsettling question. Was there a before? Time, as we understand it, began at the Big Bang. Asking what came before is like asking what's north of the North Pole. Direction loses all meaning. Some theorists propose that time itself emerged from a timeless state, like a bubble forming in a void. Others suggest our universe might be one link in an endless chain of cosmic rebirths, with each Big Bang arising from the collapse of a previous universe. Then there's the multiverse angle, where our entire timeline is just one thread in a vast, eternal tapestry of parallel realities. Yet all of these ideas share one frustrating trait: they're untestable. Without observational evidence or experiments that can recreate Planck-scale energies, we're left with philosophy as much as physics. The cosmic microwave background gets us close, offering a snapshot of the universe just 380,000 years after the Big Bang, but those first fleeting moments. They're locked behind a veil of pure energy, a curtain we may never lift. The singularity isn't just a scientific mystery, it's a mirror reflecting the limits of human knowledge. We can trace cosmic history nearly all the way back, but at the threshold of creation, the universe leaves us standing at the door, forever wondering what lies on the other side. Maybe some answers aren't meant to be found, or maybe, just maybe, they're waiting for the next great leap in understanding, hidden in the echoes of time's very first instant. If black holes are the universe's ultimate one-way streets, their hypothetical twins, white holes, would be the cosmic "do not enter" signs. Picture a black hole in reverse. Instead of matter vanishing beyond an event horizon, never to return, a white hole would violently expel everything inside, refusing to let anything in. The math allows for it. Flip the equations describing a black hole's gravity, and you get a white hole's repulsive fury. But are these objects real, or just clever bookkeeping in Einstein's relativity? The debate splits physicists down the middle. Some theorists argue white holes could be hiding in plain sight, masquerading as bizarre astronomical events. Take gamma-ray bursts, those blinding flashes of energy that outshine entire galaxies for a few seconds. Could these be the death throes of ancient white holes, finally exhausting their reserves of spacetime and spewing out light like a cosmic geyser? Another candidate, the mysterious fast radio bursts we discussed earlier. Their sudden, intense energy releases fit the profile of a white hole's outburst, though the lack of repeating signals from most FRBs makes this a shaky match. Then there's the multiverse angle. If black holes birth new universes, as some interpretations of quantum gravity suggest, then the Big Bang itself might have been a white hole event, our universe bursting into existence from the collapse of another. It's a poetic symmetry, black holes swallowing matter in one reality, white holes birthing it in another, yet the skeptics have compelling ammunition. White holes violate the second law of thermodynamics, which dictates entropy disorder must always increase. A black hole's singularity crushes matter into maximum entropy, but a white hole would somehow reverse this, spitting out ordered energy against the universe's thermodynamic flow. Plus, there's no known mechanism to form one. Black holes arise from collapsing stars, but what stellar corpse could possibly birth its opposite, the greatest irony? Even if white holes exist, we might never see them. General relativity suggests they'd be spectacularly unstable, collapsing into black holes the moment any matter tries to enter. Their hypothetical lifespans could be shorter than Planck time, a flicker so brief it makes a blink seem eternal. So are they real, perhaps not as standalone objects? But some physicists speculate that black holes might become white holes at the quantum level. Loop quantum gravity calculations suggest that when a black hole's evaporation via Hawking radiation nears completion, quantum effects could trigger a bounce, transforming the remnant into a microscopic white hole. These quantum white holes wouldn't spit out the original infalling matter. It's long gone, but they might release the information it carried, solving Hawking's infamous paradox. Whether mathematical mirage or cosmic reality, white holes challenge our intuitions about time, causality, and the universe's deepest symmetries. They remind us that the cosmos loves balance. For every trapdoor, there might just be an escape hatch waiting in the equations for someone bold enough to knock. Close your eyes and picture the universe like a movie screen, a vast two-dimensional surface where every star, every planet, even your own thoughts are nothing more than projections dancing across its shimmering surface. This isn't sci-fi, it's the holographic principle, one of the most radical ideas in modern physics. The theory suggests that everything we perceive as three-dimensional reality, the depth of space, the swirl of galaxies, the warmth of sunlight, might actually be encoded on a distant, two-dimensional boundary at the edge of existence. Think of it like a cosmic DVD. The image you see has depth and motion, but all the information needed to create it is stored flat on the disk's surface. The math behind this is as elegant as it is mind-bending. Black holes presented physicists with a paradox. If you toss an encyclopedia into one, does the information inside vanish forever? Quantum mechanics says no, information can't be destroyed, but how does it escape? The holographic principle offers a solution. Just as a hologram encodes a 3D image in a 2D film, the event horizon of a black hole might store all the information about what falls inside on its surface, pixel by pixel. Expand that idea to the entire universe, and you get a staggering possibility. The Big Bang's afterglow, the dance of galaxies, even your morning coffee, all might be shadows cast from data written on the cosmic horizon, like a movie projected from the walls of reality itself. But here's the twist: even if the universe is a hologram, we'd never know it. The resolution of this cosmic screen is so fine, a single pixel at the Planck scale, 100 billion times smaller than a proton, that our senses and instruments perceive only smooth, continuous space. It's like staring at a pointillist painting. Up close, you see the dots, but step back and the illusion of depth is flawless. Worse, the boundary encoding this information isn't just far away, it's receding faster than light due to cosmic expansion, putting it forever beyond our reach. No spaceship, no signal, no future technology could ever touch it. Why does this matter? Because the holographic principle blurs the line between information and reality. If the universe truly is a projection, then concepts like distance and volume might be illusions, emergent properties of deeper, stranger physics. Some versions of string theory even suggest the boundary isn't just storing data but processing it, like a cosmic quantum computer running the simulation we call existence. And if that's true, it raises haunting questions. Who Or what wrote the code? Or is the universe simply self-organizing, its laws emerging from the way information swirls and interacts at the edge of nothingness? For now, the holographic universe remains a hypothesis, a beautiful, maddening framework that solves some puzzles while creating others. Experiments like the holometer at Fermilab have hunted for Planck scale, jitter in space-time, a potential signature of pixelation, but found nothing. Future gravitational wave detectors might probe finer scales, while quantum gravity models keep refining the math. Until then, the principle lingers in that tantalizing space between genius and madness, a reminder that reality's true nature might be written in a language we're only beginning to decipher, on a surface we'll never see. Among the countless whispers of the cosmos, one signal stands alone, a burst of radio waves so peculiar it earned itself a name scribbled in the margin of a day to print out: the WOW signal. On August 15, 1977, Ohio State University's Big Ear radio telescope caught a 72-second blast of radiation from deep space, 20 times stronger than the background noise of the universe. The signal was so precisely tuned to the hydrogen line, a frequency of 1,420 MHz, where hydrogen atoms naturally emit, that astronomer Jerry Ryman circled it on the printout and wrote a single, emphatic word: wow. What made this signal extraordinary wasn't just its intensity, but its behavior. Unlike cosmic static or human-made interference, it was narrowband focused like a laser beam, and exhibited the exact Doppler shift expected of an extraterrestrial broadcast, rising and falling in frequency as if originating from a rotating source. For a brief moment, it seemed like the universe had finally answered our call. Then, just as suddenly as it appeared, it vanished. Despite 46 years of follow-up searches, the signal never repeated, leaving behind only questions. So where did it come from? The leading natural explanations all fall short. Comets were ruled out, none were near the detection zone at the time, a passing satellite. The frequency was pristine, uncontaminated by the telltale noise of human technology. A star system in the constellation Sagittarius, roughly in the signal's path, showed no signs of planets capable of hosting life. Even the possibility of a reflected Earth-based transmission crumbles under scrutiny. No known broadcast matched its profile. The WOW signal remains stubbornly, tantalizingly alien. Yet here's the twist: its one-off nature might be the biggest clue. The universe is full of transient phenomena, fast radio bursts, gamma-ray flashes, even neutron stars that glitch unpredictably. But none behave quite like this. Some researchers speculate the signal could have been a cosmic lighthouse, a rotating neutron star with an unusually coherent beam briefly sweeping past Earth. Others wonder if it was a fragment of a longer transmission, intercepted for just 72 seconds before the universe's rotation carried it out of earshot. Then, of course, there's the elephant in the room. Was it intentional? The signal's frequency wasn't just arbitrary. It's the universal standard for hydrogen, the most abundant element in the cosmos, long proposed as a logical hailing channel for interstellar communication. If an advanced civilization wanted to be noticed, this is exactly how they might do it: a fleeting ping across the cosmic ocean, just loud enough to make us look up. The irony: even if it was a message, we may never decode it. Without repetition, the signal carries no pattern, no structure, just a solitary blip in the void. The Big Ear telescope itself was dismantled in 1997, leaving no way to monitor the spot for follow-ups. Modern projects like the Allen Telescope Array occasionally revisit the coordinates, but space is vast and silence is the rule. Perhaps the WOW signal's greatest legacy isn't an answer, but a reminder. In a universe brimming with noise, sometimes the most profound mysteries come not from what we find, but from what we almost grasp: a voice in the static, heard once and never again, leaving us forever wondering, what if? From the Great Attractor's hidden pull to the holographic universe's pixelated edges, These 25 cosmic enigmas stand as monuments to the universe's stubborn refusal to be fully known. Each one represents a frontier where science hits a wall, where black holes guard their singularities like cosmic dragons, where dark matter whispers its presence through gravity alone, and where the Big Bang's first moments vanish behind a curtain of infinite energy. They humble us, these mysteries, reminding even the most brilliant minds that for all our telescopes and equations, we're still children peering through a keyhole into a palace of wonders. Consider how far we've come and how far we have left to go. Centuries ago, humans mapped constellations with naked eyes. Today, we trace the magnetic webs of galaxy clusters. Yet the Fermi Bubbles tower unseen above us, the wow signal remains unanswered, and the multiverse tantalizes from beyond mathematics' reach. The universe doesn't conceal its secrets out of spite. It simply operates on scales and in dimensions that defy intuition. Those voids where galaxies flee, they might be wrinkles in spacetime's fabric. Those quasars brighter than 1 trillion suns, perhaps cosmic lighthouses from when reality was young. Every unanswered question is an invitation not just to discover, but to rethink what's possible. Now imagine the tools still to come. 30-meter telescopes that dissect starlight from the first stars. Quantum sensors that feel spacetime's foam. Probes riding laser sails to the Oort cloud. Or perhaps inventions we can't yet conceive, technology that sees dark matter like headlights in fog or deciphers the hologram's code. The greatest breakthroughs often come from asking what if in the face of the impossible. So tell me, which of these cosmic riddles keeps you awake at night? Is it the cold spot's eerie chill hinting at parallel universes, the way singularities erase time itself? Or something we didn't even cover today? Drop your thoughts below, because the next big revelation might just begin with a spark of curiosity from someone watching this very video. After all, the universe writes its mysteries in starlight and static, waiting for those bold enough to listen.